Hey everybody, it's Mr. Carr again. Today we're going to be looking at 7.4c. We're looking at properties of chords. So we have a variety of relationships that occur just from having when we analyze the chords within a triangle or triangle within a circle. So the first one is in the same circle or in congruent circles, minor arcs are congruent if and only if their corresponding chords are congruent. Okay, so when I look at this diagram here, since AB segment is congruent to CD segment, then AB arc is congruent to CD arc. Okay, so this is what we know. This implies this. Okay, so that's what we're looking at here. Now, the other part of this was that in congruent circles, this is also true. So when I look at the next one, we know circle A is congruent to circle D because the two radiuses are the same. Okay, we also know that BC here is congruent to EF. So that's that and that. So the measure of arc EF is 125. What's the measure of arc BC? Well, this is intersecting the same chord as this one, like since these two match up. So that means that the measure of arc BC is also 125 degrees. It's just like the other one. Our next property, properties of chords and its diameter. If one chord is perpendicular bisector of another chord, then the first chord has to be a diameter. Okay, so here's what we have. If we have this right here where TP is congruent to PR because it's being bisected and this is perpendicular, that means that QS is a diameter. Oops, QS is a diameter. Okay, now that means that I don't know where exactly it is, but some other point is going to be the center of this, of the circle. So it passes through that. Okay, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So it just works both ways. That's the converse idea. So what we're saying was, if we know for a fact that it's perpendicular and this is bisected, it has to be a diameter. But let's say that we know for a fact we have a diameter and it's perpendicular to a chord, then we know that this has had to be congruent here. We also know that these are congruent. Okay, so we know that both TP is congruent to RP and arc TQ is congruent to arc RQ. Okay, that's it there. Congruent chords in the same circle or congruent circles. Two chords are congruent if and only if they're equidistant from the center. So this is what it usually looks like is on here. So if I draw my circle in, okay, I draw a chord. Well, actually, no, sorry, I got to draw two chords. It's a little bit tricky. So there's this chord. I'm going to make sure that chord looks about the same length there. So these two are only going to be congruent if the distance to the centers. And so we do distances, they have to be perpendicular distances. In fact, I'm just going to zoom in a little bit. Okay, the perpendicular distances have to be the same. So as long as those chords are the same distance to the middle, that means that this length is the same as that length. I can go with, I'll just call that congruent as well. That's what we're saying here. Again, equidistant means they have to be a perpendicular distance. So this is what I'm looking for in that diagram. Do we have perpendicular angles here? Are they congruent here and here? Or if I'm going the other direction, maybe these are congruent. I know they're congruent, so that I know that these have to be congruent as well. Okay, so that's what's happening in this diagram here. So in the diagram, we have AB is equal to CD, which is both equal to 12. So this equals that, meaning this FG and EF have to be the same. So F has to be equidistant to the two chords. Since they're equidistant, that means that EF has to equal to FG. Well, and since I know that, I have just some algebra set up now. I have 3x is equal to 7x minus 8. So we're just going to solve that normal, okay? Okay, sorry. So we're going to work through the algebra now. So if I subtract 7x to both sides, I get negative 4x equals a negative 8. And I divide both sides by negative 4, so I get x equals 2. Now the problem says to find EF. So EF was made up of 3x here. So EF is equal to 3 times 2, which gives me a final answer of 6. Okay. And our last concept, if two chords intersect in the interior of a circle, the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. A lot going on there. So here's what I'm here's what I'm trying to say here. Just blow it up a little bit here. Here's my circle. I have a chord intersecting a chord like this. Okay. So when I have that intersecting, I'm going to call these different segments. I'll call it A, B, C, and D. So segment A is just referring to this part right here. Segment B is right there. Segment C is right here, and segment D is right there. So the relationship here is within the same chord, A times B is going to equal to C times D. And that's it. So we're going to set up these multiplication problems based on this. Okay, so when I look at my first example, or one example here, so find the length of ML and JK. So what I have is, I'll color code it a little bit. We have NK and JN are on the same chord, just like LN and MN are. Okay, so here's my setup. I'm going to take x plus 1 and x plus 3. They're going to multiply together. Then I can take x plus 5 and x and multiply those together. And again, this is just like any other algebra problem we've done. We're going to solve this out. So I'm going to go ahead and distribute here. Make sure you're distributing properly. So x is going to multiply to both of those. 1 gets multiplied to both of those. So I'm going to have x squared plus 3x plus 1x plus 3. And I'll distribute the x as well. So I get x squared plus 5x. Okay. So normal algebra with a quadratic, I want to bring everything to one side. But notice that if I subtract x squared, they both cancel out. So it's not really a quadratic. So instead, I'm just going to put these together. So I'm going to have 4x plus 3 is equal to 5x. And then if I subtract 4x over, I get 3 is equal to x. So now I have 3 is equal to x. I want to find ML, which is made up of both x plus 1 and x plus 3. Well, I'm going to do a little differently. I'm just going to take my x and plug it here. So that's going to be 3 plus 1 is 4. This little part right here will be 3. This part will be 3 plus 5 to give me 8. And my last piece is going to be 3 plus 3, giving me 6. So I have 6, 3, 4, and 8. So ML is going to be made up of 4 and 6. So I'll just add those together to get 10. And then JK is made up of the other two, which is 8 and 3, which comes out to 11. I do want to highlight, it's very tempting for a lot of people to just start setting pieces equal to each other, okay? Or they want to take this and equal to that. It's not. It is the multiplication, okay? It's the multiplication of these segments that are equal to each other. Because you notice ML is 10 and JK is 11. Those are two different lengths, okay? So this does not necessarily equal that length for the chords, okay? And that is it for today. So that's all of our different all of our different relationships and properties we're going to focus on when chords are crossing inside of a circle. All right. And yeah, that's it for today then. Take care, everybody.